On your mark, get set, innovate. Hey there, everybody. Welcome to episode number 482 of this here electronic engineering podcast called Amelia's Weekly Fish Fry, brought to you by eejournal.com and written, produced, and hosted by yours truly, Amelia Dalton. What if we could revolutionize manufacturing and save energy at the same time? Well, this is exactly the topic of today's Fish Fry podcast. My guest is PulseForge CEO Stan Farnsworth, and we're digging into the details of PulseForge's revolutionary digital thermal processing. Stan and I investigate how this new kind of thermal processing differs from traditional thermal processing and how it can vastly reduce the amount of energy used in manufacturing. We also take a closer look at each of PulseForge's application areas, including curing and sintering, soldering, and debonding, and why Stan believes that rethinking manufacturing is crucial to future electronic design innovation. Hi, Stan. Thank you so much for joining me.
Hi there. Glad to be here with you.
So first off, for my audience who may not know, what is PulseForge all about?
Just like many technologies, that actually is a slightly longer answer. So at PulseForge Incorporated, we are commercializing what we consider to be a deep tech result. So deep technology, we've been developing this technology set for 10 to 15 years plus at this point, and we've had it on the market for a pretty good portion of that time, but it continues to evolve. And what we're doing is bringing out a very new form of thermal processing. And so when we think about industrial processes and manufacturing, most of those in some form or another require energy, typically in the form of heat, to work materials of some kind to get them into a final state. And we have developed a new way of doing that and have been focused primarily on the electronic space, different kinds of consumer electronics and wearables and AR, VR. I'm sure we'll talk about some of the applications, but the gist of it is this new form of thermal processing. I'm glad to dive into some of the weeds on that as well.
Oh, please do. Yeah. Tell me more about this new kind of digital thermal processing.
So typical thermal processing occurs in an equilibrium, steady state kind of way where think of an oven and materials go into the oven to get heated, and the entire material set that goes into the oven reaches some sort of uniform temperature. The top and the middle and the bottom, the left and the right all reach the same temperature. And in fact, typically, it's very desirable and very particular for those materials to all reach the same temperature. You wind up with a delta T problem if they're not all the same temperature, because those materials will respond differently if they're not all at the same temperature. And that can cause non-uniformities in the materials being processed, and that can result in discrepancies in the final performance, or maybe there will be some sort of stresses or warpage or something like this that might result from the materials not being at the same temperature. And so regardless of the industry, in most thermal processing, the goal very much is to keep everything at the same temperature. Now, that temperature can go up and down slowly and in some kind of measured way. But nonetheless, this is typically a process that would take minutes or hours and have to be done with this equilibration thought in mind. We are completely turning that upside down and inside out. We are very focused actually on very quickly bringing materials to their target temperature. And by quickly, I mean doing it in seconds or even milliseconds. And in fact, doing it quickly enough that the entire volume of material actually does, in fact, not get to the same temperature. So there are very much by design hot spots and cool spots. And it turns out that when we do this quickly enough, those temperature non-uniformities actually can usually wind up working in our favor. And so an example of that is what we're doing right now with soldering in the electronics manufacturing space by taking this kind of approach. And in a minute, I'll talk about how we do that, because that's part of the rub as well. But we're able to solder, and our customers and partners are able to melt and reflow off the shelf SAC 305 pick any type you want, type 3 or 4 or 5 is fine, and melt and reflow that solder on very low temperature plastics like PET or PVC and get a full, complete melt of the solder metal on low temperature plastic and get great solder joint quality with the SMT components on that plastic. And that seems like it should be impossible because, of course, the solder melting temperature is pretty far in excess of 240, 50, 260 degrees C. And these materials typically will fail at those temperatures. They'll warp, they'll melt. If you put PET in an oven at that temperature, very bad things happen to it from a product materials perspective. But because we're heating this so quickly, the solder is getting hot, the substrates are not, and we're able to complete this process. The solder is able to go to its liquidus point, and the intermetallics are able to form, and there's great wetting, and the fillets look terrific, and there's great bonding with the traces and the component leads. And then the whole system cools back down again within a second or two or three, and the plastic, as far as it knows, is unaffected. And the way we do this is by delivering energy so quickly that we're able to create a temperature gradient in the material stack. And so typically we'll use flash lamps. We've got some IP wrapped up in the flash lamps and the power supplies and the engineering to get the flash lamps to turn on and turn off again in a millisecond kind of time scale, which it turns out to be quite non-trivial. That may be another topic though. But to cycle the flash lamps on and off and to heat the surface and to put energy into the surface faster than that energy can diffuse and conduct through the volume of the material. So we're creating temperature gradients. And by carefully dosing the energy that is delivered to the surface, then we can very carefully maintain and manage that thermal gradient. And this is where we get to the digital part. We have digital control systems and digital power supplies and are very able to apply a lot of fidelity to the pulses that are delivered, make them longer, shorter, more powerful, less powerful, longer and shorter gaps between them. So there's a lot of tunability in how that energy is delivered to those materials. And we can balance and maintain that temperature gradient in such a way that in this case, we can melt and reflow solder because that's on the surface and that gets hot. And the substrate underneath that remains relatively cool because of that temperature gradient. And so we can use the tools to develop temperature gradients over 10 or 20 or 30 or 100 microns that might be hundreds of degrees. And folks that are particularly versed, going back to the problem of stresses in temperature processing, thermal processing, someone might think, well, that tremendous temperature difference can cause quite a bit of internal stress in the system. That is very true. And we can use this, for example, to flake glass. We can develop temperature gradients in glass and flake the glass. But in this material set for SMT manufacturing, that typically is not a problem. And so the resiliency of the plastics and then the very short duration of that gradient, again, we're talking about milliseconds to a second or so, typically is not enough to cause any kind of damage. That's a lot of technical background on some of the particulars of how we're doing this kind of thermal processing.
Excellent. Now, Stan, your applications are divided into three areas: curing and sintering, soldering, and debonding. So can you give my audience a bit of information on each of those areas?
Sure. And this is really one of the challenges. And this is also a characteristic of deep tech in general. So deep tech tends to be a platform tech that may have a fundamental expanse of kinds of applications. So for example, artificial intelligence is an example of a deep tech that can be used in lots of different kinds of things. Well, thermal processing is used in lots of different kinds of manufacturing and materials processing steps. The applications that we're focusing on initially are the curing and sintering aspect. And I'll start with that one. That's really where the history of our development efforts reside primarily for this over the last 5 or 10 years or so. And primarily that is around printed and flexible electronics. This really stems from our origins as a nanomaterials, nanotechnologies company. And so we still, in our partner company, Novacentrix, make nanomaterials and electrically conductive inks. And we started doing that for flexible electronics, silver inks and copper inks. And we just announced a new gold inkjet ink, which is very interesting for biomed type applications. But those inks need to be dried and sintered, typically on these kinds of low temperature substrates in order to get good conductivity. That was really the origin for how we came to realize that this kind of processing was needed, was how to get these inks to high temperatures to dry and sinter the ink particles together, but doing that on a low temperature substrate like PET or cloth or fabric, or actually a whole range of really interesting substrates that are not FR4 or glass or polyimide, shocking as that may be to many electronics industrialists out there. So developing this technology to dry and sinter those conductive inks, and to do that in typically that kind of application is typically in milliseconds. We had one of our biggest commercial applications for that was coming on 10 years ago now, but it was actually for producing cell phone displays. And where the display and consumer electronics markets were moving at that time, there was increasing need for flexibility and novel materials and embedded integrated sensors built into the displays. And that created a need for electrically conductive inks to be applied directly to the display stack. But the combination of those materials were quite unsuited for traditional thermal processing, where everything is the same temperature, because if everything was the same temperature, which was at a temperature high enough for those conductive inks to be processed, then damage would happen to that material stack. So we were able to apply our tool set to process those inks at high temperatures without damaging the display materials. And that was a pretty big global implementation of this technology set. So that continues to be a key piece for us, sintering those kinds of materials. Soldering is a relatively new application space for us. We were able to build in some hardware and software upgrades in our tool sets that took us from a processing time of milliseconds, which was all that's needed for that kind of sintering application I was talking about, but to extend that process time to seconds, which is what we see is better scaled for solder reflow. And the reason we need the longer time cycle for that is when we're sintering materials, the material particles, if you can imagine the material particles all bundled next to each other, they get pretty hot and they connect with their neighbors, and that helps the electrons move along the material. But for soldering, there's actual material reflow. Sintering is typically not reflow, it's just connecting the particles together. But in soldering, there's wetting and fillets are forming. And so we needed to keep the solder material hotter longer, just for the kinetics of the material to have the right response to do what solder needs to do. And it turns out that answer is somewhere between half a second to about a second and a half, depending on the materials and the systems. And to go from a time scale of a couple of milliseconds of processing to a second, that's a 2 or 3 order of magnitude change. So even though there's still short times, that still represents a pretty big change. And so there was some engineering that had to go into the products to be able to get to that point. We did that, and lo and behold, we're able to take fundamentally the same physics that govern the creation of thermal gradients on the sintering of conductive inks and apply that same physics forward with the idea of pulse control and multiple quick bursts of energy to get to this reflow condition with the solder. And I have to say that's going very well. And key applications for that, as I mentioned, continue to be different types of consumer electronics wearables, where the whole goal is to put the device on some kind of form factor friendly substrate, different kinds of textiles and polymers and whatnot. Automotive is another key piece for this, where we're seeing a lot of interest in the automotive space for this kind of soldering application. But there's a whole range of other applications for thermal processing of this type. And one of the other ones that we're prioritizing right now is debonding. And that really, depending on which flavor of manufacturing, that could be called liftoff or debonding. But it's the idea of a flexible substrate such as polyimide that's often used in different kinds of display manufacturing, or different kinds of semiconductor chip processing MEMS or whatnot, are often built up on these kinds of layered surfaces with the idea that ultimately that process unit product would then have to be removed from the processing platform on which it is created. And lasers are typically used right now, and they sweep and scan and raster back and forth. And create a little vapor bubble from ablating the polyimide usually, or maybe there's a little sacrificial layer in there that might be used. But the lasers will be used to pop off the display material, maybe an OLED stack that's been built on polyimide off of its carrier plate, or maybe some kind of other semiconductor MEMS or something that's LEDs sometimes are done with derivatives of this kind of technology, but to separate them from the primary plate. And one of the issues there is that the lasers are not particularly energy effective. And we'll talk a bit about the energy effectiveness and why that's important, but also they're not particularly time friendly. So they scan and raster. And what we're able to do with the PulseForge tools is because they are large area tools, they're not a tight beam of laser energy. They're broad spectrum optical flash lamp energy that illuminates an area. And so this technology is able to pop off or lift off or debond relatively large areas simultaneously, which has a lot of advantages in the products that come off, both from a production scale as well as maintaining. Back to this problem of uniformity, temperature uniformity in the target materials. And so our tools are able to flash simultaneously a large area and avoid some of these problematic edge effects that lasers can develop by virtue of being so narrow. So those are three of the applications that we continue to develop. One of our challenges, as I mentioned, is that there are really so many other kinds of applications, and our applications engineering team is really not hard pressed to find new applications. We have new folks contacting us all the time with applications of this kind of technology set, and it becomes very exciting sort of business opportunity on how we engage and partner to be able to take advantage of the capabilities of this kind of processing.
So Stan, when I was researching PulseForge, I saw that you guys say that the future of innovation depends on manufacturing differently. So I was really interested by this. Can you give me some more information about how PulseForge is advancing different manufacturing arenas?
There are a couple of key aspects of that. One that we're very excited about at a high level is the very physics of this technology uses substantially less energy than traditional thermal processing. And if you think about it, that makes sense. Instead of heating the entire material structure and all the energy that requires, we're only heating the surface. And then instead of heating a material set for minutes or maybe hours, we're only heating for milliseconds or maybe seconds. So when we actually do the math and then confirm that with actual measurements, the tools really are only using 10 to 15% or less of the energy that traditional processing would require. And so when we think about future manufacturing, and we think about decarbonizing the supply chain, and we think about the Paris Accords and trying to get to net neutral on carbon, one of the first things we can do is reduce the energy that's used in manufacturing. And we know from the Department of Energy websites and from other groups who measure and track these things that turns out that manufacturing itself constitutes 20 to 30% of the global CO2 emissions. And light manufacturing, excluding steel and concrete and whatnot, accounts for 10 to 15%. These are big numbers, and it's very noble to think. But if we can shave those numbers down using this kind of non-equilibrium, very quick technology, then we could materially have an impact on getting to our emissions goals to keep our global temperature rise down. So the sustainability piece is really important. Now, beyond manufacturing itself with the energy implications, manufacturing innovation really is hinged on a couple of other things. One is the design, what kinds of products can be designed. And from a product design perspective, it's pretty exciting. We're told, and it turns out that we are working, of course, with manufacturers, but actually increasingly we're working with product designers because they can use this kind of technology to vastly increase the kind of materials that they're able to use in their product types. And so we have meetings almost every day with design groups who are interested in understanding what the implication of this kind of technology set is on the rules and the guidelines and the normal of what is allowable on the manufacturing side. And so instead of limiting their designs to current manufacturing capabilities, they are able to expand their design options to include different kinds of materials and different kinds of arrangements and configurations of components and materials. And because these tools are increasingly already being found in manufacturing sites, either through independent manufacturers or through partner manufacturers that PulseForge is working with, there's now an ecosystem around being able to manufacture designs that are hinged and contingent on using this kind of processing technology for products that would be impossible or certainly not economically feasible using other kinds of technologies. And so when we think about opening up the door for manufacturing innovation, it really goes upstream as well to design and product innovation. It includes sustainability and decarbonizing the supply chain. It includes the ability to use recycled or recyclable or degradable materials as well. And when we think of a circular product life cycle, so all of these pieces come together, and the fact that the tools are digitally controlled, have an extremely fast response time, makes them very well suited for integration into these new smart factory industry 4.0 kinds of concepts with AI optimized process flows. And so all of these pieces come together. And so we're really, really looking at what this means for advanced manufacturing globally.
Excellent. I think it's time for your off-the-cuff question. Now, since you haven't been on my show before, you get the standard off-the-cuff. Are you ready?
I'm ready. I love it.
Okay. So, Stan, a lot of us can't have our favorite foods right now for one reason or another. We can't travel to the location. The restaurant is closed. It's on the other side of the world, maybe. So, Stan, if you could have one meal right now, it doesn't matter if you need a passport to get there or anything else, what would you have?
There's so many great choices. So fortunately, here in Austin, Texas, two of my favorite foods, barbecue and Tex-Mex, are pretty prolific. So if anyone wants tips on barbecue and Tex-Mex in Austin, I'm glad to talk about that. Globally, I am always a sucker for Italian, and I got into a little bit of Venice has a little particular subset of Italian food. And so I'm always happy to eat in Venice. And then also there's something about fondue in the Swiss Alps. I know that's not a very spring or summer kind of topic, but something about fondue in the Swiss Alps is really, really hard to reproduce anywhere else in my experience. And so as we look to the onset of summer here in Austin, maybe that's why I'm already thinking about escaping to the Alps and maybe finding some fondue.
I love it so much. That is my first Venice, Italy answer. However, I've gotten a fair amount of Italy answers, but not specifically Venice yet. Good job, Stan. Well, I think that's all I have time for today. Thank you so much for joining me, Stan.
Thank you for the opportunity, and I look forward to continuing to track your upcoming podcast.
Thanks so much. Hey, have you checked out EE Journal on social media yet? Well, you should. You can find us at facebook.com/EE Journal. If you're into Twitter, you can monitor our tweets at EE Journal TFM. And don't forget, if you would like to follow my personal Twitter account, check out Amelia D 1978. And hey, if LinkedIn is more your thing, sure, I dig it. You can follow us or me on LinkedIn as well. And we have a YouTube channel, youtube.com/EE Journal. Folks, it is chock full of all kinds of techie videos, including our very popular Chalk Talk webcast series hosted by me. And you can subscribe to our EE Journal YouTube channel as well. Also, by clicking the links below the player on this week's Fish Frying page, you can subscribe to this here podcast through Spotify, Podbean, or Apple Podcasts. And remember, if you'd like to further support this podcast, please leave me a review on Apple Podcasts. And 5 stars, please. Also, if you'd like any further information about the stories covered in today's show, just head on over to eejournal.com and look for this week's Fish Frying page. Thank you everyone for tuning in. If you know of any cool new technology or heck you just want to chat, shoot me a line at Amelia, that's AMELIA, at eejournal.com, or post a comment on our forums on EE Journal. For the week of May 20th, 2022, I'm Amelia Dalton, and you've been fried.